Hi everyone, I'm Soo-Young Choi, and today I'll go over nuclear spins in silicon. Before we begin, I'd like to briefly introduce the format of my presentation. Essentially, it follows the flow of questions I encountered while processing research on this topic, along with the corresponding answers found in the research papers. Additionally, I've organized the development of related papers in chronological order. Throughout, my main focus has been on the potential scalability of nuclear spin quantum computers and approaches to achieving higher fidelity in gate operations. The first question I had was, what is the first version of the physical implementation of a qubit? In 1995, David Wineland's group made significant advancement in demonstrating the feasibility of trapped ions as qubits. They demonstrated the first quantum logic gate operation with trapped ions, laying the foundation for subsequent research in the field. These early experiments paved the way for further developments in quantum information processing using various physical platforms, including semiconductor, quantum dots, and etc. In 1998, Kane first proposed a silicon-based nuclear spin quantum computer using nuclear spins of individual phosphorus atoms in silicon as the qubits and donor electrons to mediate the coupling between qubits. Let's delve into the nuclear spin qubit configuration in Kane's scheme. First, when you look at figure 1, A and J are gates, and these gates are applied in experiments involving electron spin resonance or nuclear magnetic resonance techniques, which are commonly used to manipulate and read out the quantum states of nuclear spins in silicon. The role of the A gates is to precisely tune the resonant frequency of the nuclear spin qubits to match the frequency of the microwave or radio frequency pulses used for qubit manipulation and readout. By applying appropriate microwave or radio frequency pulses through the A gates at the resonant frequency of the qubits, we can perform operations such as qubit initialization, coherent manipulation, and qubit readout. To help your understanding, I attached the video that helps me a lot. In this video, B naught equals to DC magnetic field of 2 Tesla, and the direction of AC magnetic field is east to west with 10 to the power of minus 3. Here, it shows the nuclear spin of phosphorus. Now, J gate controls the electron-mediated coupling between adjacent nuclear spin. The latch, which is represented at white dot at here, is typically located at the interface between a gate electrode and the silicon substrate or the insulating layer that separates the gate electrode from the silicon substrate. Next, figure 2 shows that J gates vary the electrostatic potential barrier between donors to enhance or reduce exchanging coupling. That is represented in here. Next, in figure 3, the arrow up and down notation is used to represent the electron spin state, which is 3 triplet states and 1 singlet state. And the number 0 and 1 notation, the nuclear state. Only singlet state electrons can make transitions into states in which electrons are bound to the same donor. Electron current during these transitions is measurable during capacitive techniques, enabling the underlying spin states of the electrons and nuclei to be determined. Now, let's talk about the 4 challenges to building the computer presented in his paper. The most obvious obstacle to building the quantum computer presented above is the incorporation of the donor array into the silicon layer beneath the barrier layer. This challenge of fabricating large arrays of donors was addressed by using a different type of qubit device, and PLOS paper utilizes that method. Then, are all aspects of the challenges and drawbacks of nuclear spins in silicon covered in this paper? Of course, the answer is no. So as to answer the question, we have to look at the advantages and drawbacks of nuclear spins in silicon compared to other qubit implementations. First, nuclear spins in silicon can have long coherence times, which is essential for performing quantum operations without losing information to the coherence. Silicon has a relatively low concentration of nuclear spins compared to other materials, reducing interactions that can cause decoherence and allowing for longer coherence times. Secondly, silicon is the foundation of modern semiconductor technology, and extensive infrastructure exists for processing and manufacturing silicon-based devices. This compatibility could enable the integration of quantum computing devices with existing semiconductor fabrication techniques, potentially leading to scalable and manufacturable quantum processors. Next, the first drawback is limited quantum gate fidelity. Achieving high-fidelity quantum gates, essential for performing quantum computations accurately, can be more challenging with nuclear spins in silicon. The weak interaction with external fields can lead to slower gate operations and lower gate fidelity compared to other qubit implementations. So next, while silicon has relatively low magnetic noise compared to other materials, nuclear spins can still be susceptible to environmental noise sources, such as magnetic field fluctuations and temperature variance. Especially, temperature is an important factor for maintaining qubit coherence, and usually, nuclear spins in silicon are operated on approximately 0 Kelvin Fahrenheit. This is why room temperature quantum bit storage exceeding 30 minutes using ionized donors in silicon is astonishing. There are lots of research studies on temperature variance, and subsequent research has provided us with better results. However, in terms of potential for scalability and gate fidelity, why haven't we achieved as much progress as we have with long coherence times? Where should I start to build scalable quantum systems? First, we should know about the gate-based dispersive sensing. The important feature of gate-based dispersive sensing is that we need to know here is that it reduces the number of electrodes needed on the chip by utilizing the interaction between the qubits and nearby control gates to indirectly measure the qubit states. This method eliminates the necessity for individual readout electrodes for each qubit, thereby decreasing the total number of electrodes required on the chip. Fogarty's paper highlights the limitation of the current approach and proposes an alternative method that offers additional benefits, which is compatibility with dispersive sensing and improved scalability. Currently, single-shot readout in silicon systems relies on a method called single-spin selective tunneling to a reservoir. This method involves transferring information from the qubit to a reservoir, a separate storage area. While this reservoir-based readout approach is convenient, it's not ideal for a gate-based dispersive sensing. As I mentioned, dispersive sensing is a method for measuring qubits indirectly without directly affecting them. This method is advantageous for large-scale quantum computing systems because it reduces the number of electrodes needed on the chip. The author suggests using a different readout method based on polyspin blockade in a structure called a double quantum dot. This method is compatible with dispersive sensing and has additional benefits, such as enabling parity readout for error detection and correction in quantum computing. The proposed readout method, based on the singlet-triplet basis of the double quantum dot, can achieve high fidelity spin readout at lower magnetic fields compared to the current method. This allows for qubit control at lower microwave frequencies, which is beneficial for scalability. First, let's talk about the device structure of PLA, which are familiar with from our class. In PLA's paper, they use an on-chip all-electrical detection method for both electron and nuclear spins using a compact nanoscale device in Figure 1a, compatible with silicon metal oxide semiconductor fabrication standards. The device consists of ion-implemented phosphorus donors, tunnel coupled to a single electron transistor that represented in the red circle. In this reservoir-based readout, each qubit typically requires its own dedicated readout electrode. These electrodes are used to manipulate the electron reservoir and measure the resulting current flow, which provides information about the qubit state. Therefore, for n qubits, reservoir-based readout would require n separate readout electrodes, each connected to an individual qubit. Now, let's look at the Figure 2, the device structure of Fogarty. Here, the basic device structure and operation are much like in PLA, which includes an integrated single electron transistor sensor, which is represented in this red circle. In order to combine the ability to address individual spin qubits using ESR, electron spin resonance, with the voltage pulse-based detuning control, and high fidelity readout of pairs of spins in the singlet-triplet basis. The main difference is that electrons are populated into the two quantum dots, this quantum dot 1 and quantum dot 2, using positive voltages on gates 1 and gate 2, which is represented in here with Figure 2a. Each qubit is controlled by these gates, and these gates can also serve the purpose of indirectly measuring the qubit states. In gate-based dispersive sensing, instead of n separate readout electrodes for n qubits, only a single shared readout resonator and a few control gates are required for the entire system. In addition to reducing the number of on-chip electrodes as mentioned earlier to achieve scalability, efforts to create scalable quantum systems continue from various other methods. For instance, in 2019, Zhao et al. Demonstrate low-field operation of metal oxide silicon quantum dot qubits by combining coherent single-spin control with high fidelity, single-shot, polyspin blockade-based readout. And these singlet-triplet readout enables high-fidelity spin state measurements in much lower magnetic fields without the need for reservoirs. Looking at research from Fogarty, Zhao, and others previously presented, the used methods polyspin blockade, coherent exchange oscillations, electron spin resonance, nuclear magnetic resonance are not novel. But the application of all these methods on one device is new and very interesting. Therefore, By consistently researching and integrating existing methods, scalability of the quantum system can finally be achieved. Thank you for listening.